तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In an earlier course on digital circuits, we would have seen the design of combinational logic. There the approach would have been to minimize the number of gates used in the design. There are conventional techniques such as Karnaugh maps to reduce the number of gates to be used in implementing a given function. This conventional technique is good provided the circuits are simple, but today's technology, we design circuits which are very large, extensive, of course complex. Complexity can be always implemented with whatever gates available, but the size of the circuit is of concern here. If you have a huge circuit to be implemented using gates and Karnaugh maps, the design becomes extremely difficult. Another thing we would have learned in the Karnaugh map approach is, even though the circuits use AND, OR and inverters, sometimes you are asked to manipulate the circuit to use a specific type of gates, such as NAND gates for example. So, in that case what you do is to take the simplified function using Karnaugh maps and manipulate it to use a given type of gate like NAND gates. So, these techniques, as I said, are good for small circuits, but when the circuit becomes larger, as in today's technology, we need to look at other methods. These other methods revolve around the available components. So, you decide on what hardware you are going to implement the circuit and try to map your circuit function onto the available hardware. For example, today's technology like field programmable gate arrays, you have a capability of 100,000 gates, 10,000 gates, 4,000 gates, etc. And when you look at the function, I will simplify it such that it can be fitted into that available gate. But before going to that level, because that is the scope of this entire course is on IC design, digital VLSI design. Before going to that level, I want to take you one step further than the gate level implementation. Mapping of the given function onto an available hardware or given hardware, that is the theme of the VLSI design, that is the sort of an emphasis on VLSI design. In order to go there all the way, before going there all the way, we will take one step at a time. We will look at some of the smaller, less complex components, hardware, and see how our circuits can be mapped onto this. As an example of this approach, we will take multiplexers. So, we will talk about multiplexer based design as an example of fitting a design on an available hardware. So, let me say multiplexer based design. All of us know what a multiplexer is. A multiplexer is a component which has several inputs and one output, let us say 4 inputs and one output, and which of these inputs gets connected to the output depends on the inputs known as selector inputs. So, in a 4 to 1 multiplexer where there are 4 inputs and one output, we need to have 2 selector inputs so that one of these 4 can be selected at a time to the output. So, let us call these inputs I0, I1, I2, I3 as inputs 0, 1, 2 and 3, and the selectors as S0, S1 and S0. On the output F, we can write the function F as I0 if both these S1 and S2 are 0 or low. So, that is S1 bar, S0 bar, I0, or if it is 0, 1, that is S1 bar, S0, then it is I1 which is the output. Then if the input is 0, 1, 1, 0, that is S1, S0 bar, output is I2, and finally when both are 1, output is I3. This is a multiplexer which selects from a given number of inputs one of the output, one of the given number of inputs, one of the inputs as the output, and the output of the selected depends on the selector combination. Now, I can use this component to design a logic, combination logic. Now, this is not a gate approach, but it uses gates because you know that multiplexer cannot be built without gates. If you break into the multiplexer and see what is inside this multiplexer, you still will find AND gates and OR gates. Like any other combination logic, everything can be reduced to a basic set of AND OR inverters or a universal gate such as a NAND gate or a NOR gate combination. But for the designer, he does not have to know the inside of this component. If the input output specifications of the component is given, the designer should be able to fit in the required design into this piece of hardware. This is what is known as a level higher than the gate level, a level in which the hardware is given to you and that hardware should be used to fit in the given design. Of course, sometimes it may not be able to fit in because your design requirement is larger than the available component. In that case, we will have to see how to do that. That we will see later on. So, as continuing this example, let us try to implement a 1-bit full adder. All of us are familiar with this component, 1-bit full adder, and see how we can implement the 1-bit full adder using multiplexers. So, let us try to get a 1-bit full adder whose inputs are A, B and carry. So, I will call this ith bit of A, ith bit of B and Ci minus 1, the carry from the previous stage, and the output sum carry, ith bit, ith stage carry, ith stage sum, and this is a full bit, 1-bit full adder, and all of us know the truth table for this. Ci would be 0, 0, 0, 1, 0, 1, 1, 1. This is a well known truth table. You might have seen it in umpteen number of books, who might have studied it in your earlier course, and you also know how to implement it using gates. You will draw the corner map, one corner map with A I, B I and C I minus 1 as inputs and S I as output, an 8 cell corner map. Similarly, you will draw another corner map with A I, B I, C I minus 1 as input and C I as the output, again an 8 cell corner map, and then you will simplify them, and then you will implement these two simplified functions for S I, C I and implement them using gates. And if somebody says use only NAND gates and OR gates, you will further do manipulation and do that. That is not what I am going to do. I am going to straight away see if it can be implemented using an available component. Now I am told by the person who has given this problem to me that use only multiplexers. So then if I have a choice of using the multiplexer type, I would go with, because there are 8 inputs and 1 output, naturally I will choose a multiplexer with 8 inputs I0, I1, I2 etc. up to I7 and 1 output F, and when you have 8 inputs I need 3 selectors S2, S0, S1 and S0. So that will be the simplest possible implementation. So I am going to use a multiplexer with 8 inputs, 1 output, 8 to 1 max, and the output F is nothing but Si. The inputs are 0, 0, 0, the output is 0, like that. So I need to connect to my selectors, my AI, BI, CI minus 1, and connect to my 8 inputs I0, I1, I2, I3, I4, I5, I6, I7, these values as it is. So 0, 1, 1, 0, 1, 0, 0, 1. So whatever is the combination, corresponding output input will be connected to the output. For example, if you take the combination 1, 0, 1, 1, 0, 1, A is 1, BA is 0, CA minus 1 is 1, output should be 0. So 1, 0, 1 correspond to I5, I have connected 0 to it, output will be 0. This is the simplest implementation. I have not reduced the corner map, I have not drawn the corner map, I have not reduced it, I have simply mapped on the available hardware, namely the multiplexer, my given design specification. Very straightforward and simple. And the another multiplexer will be required in order to finish the job, to do my CI. So I will use the same inputs as selectors here, S2, S1, S0, S2, S1, S0, I0, I1, I2, I3, I4, I5, I6, I7. So in this case I will put 0, 0, 0, 1, 0, 1, 1, 1. So I will not draw this in detail, you know what I mean. So this gives me my CI output carry. That means 2 outputs SI and CI corresponding to the 2 outputs of the full adder with 8 inputs I can implement using 2 8 to 1 multiplexers. So this is fitting into the available hardware the design specs. Today that is gaining momentum, because this is only a simple example. Full adder, who would do this? Probably I will do exclusive OR gates and simple AND gates as you are used to doing in your previous course. You probably may think that is simpler than this, but think of this example growing and larger number of inputs and more complex functions. So the mapping of the available components, especially the type of circuits today we are talking about, are circuits whose functional equivalent functionally they are equivalent to thousands of gates, tens of thousands of gates, hundreds of thousands of gates. When you have to design a controller or something whose functional complexity is equal to tens of thousands of gates, you will go for this type of ready-made component, fitting in the design into the ready-made component, rather than going and writing a Carnot map or whatever is the other technique by which you can simplify and say so many gates are going to be used. It is not gate optimization that is important today, it is the fitting into our available hardware the given design. That is the essence of the IC design, VLSI design. In an integrated circuit design, the essence is to fit into the available or the given hardware as much functional complexity as possible. So, we can optimize it, of course. I am going to show you, this is a waste of 2 8-to-1 multiplexers. This is approach I want to show you, but then this may not be the best way to do it. Can I optimize it? Instead of using 2 8-to-1 multiplexers, which is I would say is a overkill for this simple problem, can I do it in a slightly simpler way? Let us see. Now, instead of having 3 variables as selectors and 8 inputs, if I now have only 4 inputs and 2 selectors, suppose I am put a restriction, I am put an extra restriction by the specifier of the problem. The person who specified the problem to me says use multiplexers, but do not use 8 input multiplexer, use only 4 input multiplexer. Like in the Carnot map case, we said if you are given free ride, you would use AND gates, OR gates, inverters. But if the person comes and says use only NAND gates, we will do some further manipulation. The same concept here, I am going to use 2 4-to-1 multiplexers. These are I am allowed to use. And this I will get SI out of this, I will get CI out of this, and there are only 2 selectors, S1 and S0. Now the question is, out of 3 inputs A, B and C, which of these 2 I will use as selector inputs? I can use any, but let us say I will use A and B. Let us say I am using AI, BI. As my selector inputs. So now instead of going to this truth table and designing line by line, I am going to go to the truth table where AI, BI are both 0, because there are only 4 combinations possible. AI, BI both 0, AI 0, BI 1, AI 1, BI 0 and both 1. There are only 4 combinations possible, 0, 0, 0, 1, 1, 0, 1, 1. So, I will have to look at those 4 combinations. I am going to identify those combinations here. This will become AI, BI both 0, 0. Then the next combination is third combination will be, and fourth combination is. Now with this, how am I going to do this? Earlier I had one row corresponding to each input. So looked at the first row, found that the input as 0, connected to 0. Second row found the input to be 1, I connected 1 to that. That is easy mapping. Now the mapping is, you have to do a little more exercise here. Now these 2 rows together correspond to the first input here, where AI, BI both 0. That means in order to get SI is 0 when AI, BI are both 0, SI 1 when AI, BI both 0. What distinguishes this row from this row is CI value. If CI minus 1 is 0, the output is 0, CI minus 1 is 1, the output is 1. So that means output SI is same as CI minus 1. So instead of connecting a 0 or a 1, I am going to connect CI minus 1. that is my input. I go to the second combination. If Ci minus 1 is 0, I get output 1, Ci minus 1 is 1, I get output 0. So, this would be Ci minus 1 bar. Likewise, the third case, it is Ci minus 1 bar. And finally, when both are 1, A and B are both 1, when Ci minus 1 is 0, the output is 0, Si is 0. When Ci minus 1 is 1, the output is 1. So, this is same as Ci. So, now I have added that extra restriction of using only 4 to 1 multiplexer rather than 8 to 1 multiplexer and gotten this. I can now repeat it for this. For this case, both are 0, Ci is 0. This is Ci is 1 if Ci minus 1 is 1. This is 1 if Ci minus 1 is 1. This is 1 when both are 1. In this case, whether Ci is 0 or Ci minus 1 is 0 or Ci minus 1 is 1, both cases the output is 1. So, now this case I have 4 inputs, 1 output, 4 inputs, 1 output. I am able to get a Si function out of this, Ci function out of this. There are 2 significant things you have to see in this design. One is that I have reduced the size of the multiplexer from 8 to 1 to 4 to 1. I am not using any extra logic per se, but of course, there is only one thing. Ci minus 1 is an input to me. I can use that input straight away. But only thing there is an inverter required, because Ci minus 1 requires here in true form, in the complement form. True form, complement form, true form. So, I need an inverter. Maybe I will have to replace this Ci minus 1 by an inverter. These are inverters. Yes, whereas in this case there is no inverters required. By just adding one extra inverter, I have reduced the design from 2 8 to 1 multiplexers to 2 4 to 1 multiplexers. 2 4 to 1 multiplexers. The other significant feature of this design is that normally these multiplexers come in dual packages. You can't buy a single 4 to 1 multiplexer in the market. You have to buy this as a twin package. So, in one chip IC, you will get 2 of those 4 to 1 multiplexers. So, anyway, since you are going to buy a package of 2 4 to 1 multiplexers, you can actually use both of them and get the entire design rather than buying 2 different ICs. That is another significant feature of this. This tells you how to proceed with an available components. As an example, multiplexer I took as an example, full adder I took an example, so that the concept is clearly understood and it is also simple. Think of this as a bigger and bigger problem. As the problem grows, we can get more and more complex circuits using multiplexers. It can be proved that, just as we have proved in our earlier combination logic course with gates, all logic functions can be implemented using AND OR inverters to start with, and further can be simplified to NAND gates and OR gates. It can be proved that all the combination logic can be derived using multiplexers. So, today there are ICs available with huge number of multiplexers inside them, and you can program those multiplexers and interconnect them in any way you like in order to realize any major function. Any complex function that you want to implement today in IC, in VLSI you call it, you take a sea of multiplexers, an array of multiplexers, several multiplexers in one package. These are independent multiplexers, you can interconnect them the way you like to implement various functions. Of course, it can be done automatically, there are programming, we will see some of those things later on in this course. And this is a simple example. Multiplexer is not the only component, there are other components. Next, one more component which is very frequently used is a decoder. We look at a decoder. Again, you might have heard of this component in your previous course on digital design. A decoder is a circuit which has several inputs and several outputs, and the outputs are related to the input by a code. For example, if we take a decoder with, let us take a simple case of 2 inputs and 4 outputs. This is called 2 to 4 decoder. That means you have 2 inputs and 4 outputs. Let us call these inputs A and B. Outputs as O0, O1, O2, O3, meaning output 0, output 1, output 2, output 3. O0 is when both are 0, this output is high and rest are low. So, this is A bar, B bar. If A is 0 and B is 1, that is A bar B, output 1 is active, output 2 is active, and this is 1 and this is 0, and finally when both are 1, this is active. This is an example of a decoder. Again, a packaged IC which is available to you in the market, you can use that to implement a given logic function rather than going to the gate level and minifying it, simplifying it, right. So, let us see how to do the same problem of the full adder using a decoder. What is the size of the decoder we will use? I would use, let us say, an 8 to 1 decoder, I mean 3 to 8 decoder. I will have 3 inputs. I will call this A, B and Ci minus 1, Ai, Bi, Ci minus 1 are the 3 inputs to the decoder. And 8 outputs. Now, this is a simpler design than the multiplexer based design. Now, we know that this decoder is giving you outputs corresponding to the combination of the inputs. If all these inputs are 0, you will have an output of this high. I will call this O0, 1, 2, 3, 4, 5, 6, 7. So, whichever is the combination of the input, corresponding output will be high and rest of the outputs are low. Now, for a sum Si, we need the outputs 1, 2, 4 and 7. It was 1, 2, 4 and 7. So, the output will be high whenever these combinations are occurring, these outputs will be high, and the sum is nothing but an OR of this. The sum is this or this or this or this. So, all I need to do is to put an OR gate at the output. Tie them together and call it Si, and for the carry we want the outputs 3, 5, 6 and 7, which is 3, 5, 6, 7. Take these outputs and put them into another OR gate. This is Ci. So, one simple 3 to 8 decoder with 2 OR gates, I can make the full adder circuit implemented as given in this truth table. there is one catch though. The catch is decoders generally do not come with active high outputs. In decoders generally when you buy in market the commercial decoders, the outputs are selected based on the input combination, that is all right, but will not get a high. What I assumed is, in this case for example, if both are 0, 0, 0, the output this will be high and rest of them will be 0. If this is 0, 1, I assume that this will be 1 and rest of them will be zeros. That is called active high, that is output is high when an input is chosen, corresponding input is chosen. But what happens in an actual device, commercial device, outputs are active low. That means when I choose a combination, the corresponding output will be low and rest of the outputs will be high. For example, if this is 0, 0, 0, O0 will be 0 and all others are high. If for example, if we take 0, 1, 1 which is correspond to combinations 3, O3 will be low and all others will be high. This is called active low combination. That means in order to implement, I will not get this as A0 B0, this will be A0 in a real circuit, in a real commercial decoder, this is active high. When you go to active low outputs, in this A and B, this will be AB, A bar, B bar, bar. This will be A bar, B bar, A bar, B bar, this will be A, B bar, bar, and this will be A, B bar. Which means this is by applying De Morgan's theorem, this will be A or B, this will be A or B bar, this will be A bar or B, and this will be A bar or B bar. So what we get is not this but this. That has to be factored into our design of the full adder. That means if I use that logic here, my gate combination will now be changed. So instead of this being the outputs, using my active low outputs, if I use my input as AI, BI, CI minus 1, this will be not O0 but it is O0 bar. This will not be O1 but O1 bar, and then this will be 2 bar, 3 bar, 4 bar, 5 bar, 6 bar, 7 bar. How are we going to get the same function implemented? How are you going to get the full adder using this 3 to 8 decoder with active low outputs? 3 to 8 decoder with active low outputs, inputs being AI, BI, CI minus 1. How am I going to get my SI? How am I going to get my CI? That is the question. That means I have to do some manipulation in the output gates in order to get the outputs, actual outputs, that will be. Now instead of getting, what I want is, let me write it here, what I want is the sum is, outputs will be 1 or 2 or 4 or 7. This is my output requirement from the truth table of the adder, full adder. Now, if I want, if this also can be written as 1 and 2 and 4 and 7 bar, 1 bar, 1 bar and 2 bar, 4 bar and 7 bar. If I do that, if I take the corner De Morgan's theorem, this will become 1 or 2 or 4 or 7. Since I have 1 bar, 2 bar, 4 bar, 7 bar, all I have to do is to take this, take this, take this and take this and put them into a NAND gate. It may say. Likewise, my carry would be 4, 3 or 5 or 6 or 7, which is same as writing 3 bar and 5 bar and 6 bar and 7 bar whole bar, which is equivalent to saying now 3 bar, 5 bar, 6 bar, 7 bar. So, I will take this, take this, take this, put in an AND gate. So, I got my full adder, 1 bit full adder using a 3 to 8 decoder with 3 inputs A, B, I, C, I minus 1, output S, I minus C, I with active low outputs for the decoder. We have seen the example using the decoder as another way in which hardware can be implemented, wherein you fit in the design specification to the available hardware. Multiplexer was the first example we took and decoder was the second example. I just took the decoder example to show you multiplexers are not the only components in which you can fit in a design using the available hardware. But we will revert back to switch back to the multiplexers for a minute again to see some other interesting features of this multiplexer based design. Today in the what is known as the FPGA based designs, FPGA stands for field programmable gate arrays. We saw this term in the introduction and we will see a lot more of this in the future lectures. In the FPGA, lots of functions are available on a single chip and you have to map your design to these functional blocks within the chip, and multiplexer is a major component, a major functional block available in these FPGAs. So, for that reason I want to go back to the multiplexer and tell you something more interesting about it. The example we took in the multiplexer case was a 1 bit full adder. First we did it using two 8 to 1 multiplexers, then we said it is a overkill. We took the same example and implemented using two 4 to 1 multiplexers. It's a reasonably reduced size and also because of the fact that a single package can accommodate two 4 to 1 multiplexers. But in a given environment of an FPGA or a large IC design, VLSI design, you may not have multiplexers of different sizes available to you, whereas functional requirements may be different. There may be several functional requirements requiring multiplexers of different sizes, but within a single chip of the FPGA, only one type of multiplexer may be available. That means a given number of inputs, given number of outputs, same type of function, several of them, in fact hundreds and thousands of them available, but all of them with the same variety, same type. Whereas my functional requirement would be different. In some cases I may have fewer inputs and one output, in some cases I may have large number of inputs and one output. So, how do I tailor or reduce my input output specification to the type of multiplexers available on the chip. This we will see from an example. I will give you a function which will require normally 8 to 1 multiplexers, 3 inputs and 1 output, and I am further told that I can only use 2 to 1 multiplexers, 2 inputs and 1 output, with of course no restriction on the number. Of course, if we put also the number restriction, sometimes it may be able to match the required restriction, many times we may not be able to match the restriction. So, let me not have any restrictions on the number of multiplexers I will be allowed to use, but I will use the type of multiplexers as 2 to 1. So, let us take an example of a function f which is xy plus xz plus yz. This is a function I want to implement. How many variables are there in this? 3 variables x, y and z. So, normally I would say I will use an 8 to 1 max with I0 to I1, I7 and inputs x, y and z, output f. Then I can also say that you do not want to have 8 to 1 multiplexer, can I reduce it to 4 to 1 multiplexer and all that, as we did in the previous case. But in this case what I am going to do, in this example what I am going to show you is, I want to do the same implementation not using 8 to 1 multiplexers, not using 4 to 1 multiplexers, by only using 2 to 1 multiplexers. So, I am going to put a further restriction on this. Use only 2 to 1 maxes. I am not giving you another restriction on how many you should. Of course, you can also put a restriction. There are theoretical limits of how many, what is the minimum number of multiplexers required for a given function, but I am not getting into the theory of that. I am going to say use only 2 to 1 multiplexers. The idea is to reduce such that you use as few as possible. Even though I am not giving you a number as a restriction, I expect you to do it using a minimum number of 2 to 1 multiplexers. So, for that what I am going to do is I am going to rewrite the function f. I am going to select 2 to 1 multiplexer means there can only have one selector variable. There are 3 variables x, y, z. So, I can have x, y or z as the selector variable each case, and one of these variables can also be an input variable. So, I will have to use any one variable the first stage, and then another variable in second stage, and the third variable would be the input variable. So, let us first rewrite it using x as the selector variable. Supposing I rewrite this as x bar yz x y z yz. Let us see whether it is right. See, this x bar yz combines with x yz to become yz, which is this term. Then there is xy term, there is xc term. That means I have succeeded in rewriting this f in this form. That means I can use a multiplexer with 2 inputs controlled by x as the selector input. When x is 0, this will be the input which will be connected to the output of the multiplexer. When x is 1, this will be the input connected to the output of the multiplexer. But this again will require further gates. Yz can be realized only using gates, yz can be realized only using gates, and y or z or yz requires another OR gate. So, this is not a good solution, even though I will use only one multiplexer, which this is possible with x as the input. This is I0, I1, this is correspond to x bar, this is correspond to x. So, this will be yz, this will be y or z or yz. but this is not what I had in mind, because this again requires a 2 input AND gate, this requires a 2 input AND gate and a 3 input OR gate. So, can I do further simplification, so that I will not have this gate combination, I will have only a single variable as input, either x or y or z. X is already taken care of, either y or z as the input variable, and can I redo it. Now, so that means I am going to do one more thing, I am going to call this function a, the whole function yz, and call this whole function y or z or yz as b. I am going to call this b, I am going to call this a, and I am going to write a and b individually in terms of y. So, I am going to write a as y bar, is this right? Right, because a is nothing but yz, so it is y bar 0, which is 0 yz. So, this term is taken care of completely. Then I am going to write b as y or z or yz, I am going to write b as y bar z or y 1 plus z. Now, this will happen, this will be, this can be expanded to y bar z y yz, and you know that y bar z plus y is same as y r z plus yz. And also, since we know 1 plus z is z, I can rewrite it b again as y bar z y into 1. Now, that means I now have a and b expressed as multiplexer in expansions with y as the selector variable. So, it can be implemented in the first stage as the a function will be obtained by giving y as the selector, variable, 0 as the first input and z as the second input, and the second multiplexer which will implement b will have z as the first input and 1 as the second input. This will be b, and together they can be implemented using a third multiplexer with x as the selector input, and this is the output. So, all of them are 2-to-1 muxes. So, in effect what we have done is a given function which would have normally gotten required, which would have normally required 8-to-1 multiplexer, we have now redone it using 3 2-to-1 multiplexers by rewriting these equations such a way that we only have 2 inputs for each of the multiplexer and 1 output, but it required 3 multiplexers. As I said, in FPGA there are so many multiplexer functional blocks of the same type, the number is not a restriction, but we can go on adding any number of multiplexers in order to realize the function. So, that is the essence of VLSI design. A huge function will be given several inputs, several outputs, there may be several functional blocks with variable number of inputs and variable number of outputs, all of them should be mapped onto a uniform hardware where a uniform type of functional block will be available, and that will be used for synthesis. We will stop with this, and tomorrow we will see how to do the same type of implementation using programmable logic device.